Hello, my name is Federico Palacios, and I'm here today to present ROAR's end-to-end reinforcement learning project. Here presenting with me today is Xuan Liu. Xuan?
First, briefly introduce our project. We have developed an end-to-end reinforcement learning agent to do self-driving based on the existing color simulated environment. This means our model will receive information about its surroundings and directly choose what action to take. Unlike previous traditional controller models like PID, our agent no longer needs to be manually designed or tuned the parameters of controller. Only through the rewards we have preset for the map, the agent can learn how to drive by itself. Additionally, our reinforcement learning agent handles multimodal inputs, including the vehicle's velocity, location, and the occupancy grid map from the environment, which are more complicated than before.
So let's discuss the inputs to the model. On the left, we can see our perceived input, what we want the car to understand. The light blue represents the vehicle itself. The black lines represents the border of the track and the walls. These yellow lines represent checkpoints or reward lines that the car wants to reach, right? The occupancy map data is separated from the reward data. That way, our model doesn't have to work harder to understand the difference between the two. They're then stacked together, and one stack of 2 by 224 by 224 represents one frame in time. We take 4 different frames in time and stack them together to create our input data. This input data is then passed into our model architecture. Each frame of data goes through a ResNet before all 4 frames are then compiled by an LSTM to make sense of the sequence. After passing through a fully connected layer, our PPO, or Proximal Policy Optimization algorithm, then looks at the features given and the reward to make a decision about what to output into the Carla controls. Our output consists of throttle, steering, and braking. Throttle and braking range from 0 to 1, while our steering ranges from -1 to 1. Our action space for this output is continuous for all 3 actions. Next, let's talk about the reward structure for our model. We reward crossing a checkpoint, the average speed between checkpoints, and keeping the steering to a minimum. This encourages the car to go further, go faster, and to not overcorrect so much so we don't see as much wobble on the track. We penalize crashing, slowing down, and the time spent on the course. This keeps it away from the borders and prevents it from using the brake too much to turn. The last penalty can be thought of as hot water for our reinforcement learning model. This encourages the model to spend as little time as possible in any single iteration.
At the beginning of the training, the car just went left and crashed the left border at the end. It will try to explore the environment with different actions to collect trajectories for the training afterwards.
Next, let's take a look at what our model looks like after training for several thousand iterations. At this point, it's still a little early, but we can begin to see signs of progress. As the vehicle moves forward, you can see that it is making an attempt at staying at the center of the track. As it sees the borders, it does try to avoid them. Here we have a close call in which it does approach the border, but it understands that it needs to move away. After driving forward for a bit, it almost approaches another border and overcorrects before slamming into the wall again. As we continue to train our model, we hope to see it exhibit more of this behavior where it maintains the center of the track and avoids the walls. And with that, I'd like to wrap up our presentation. Thank you very much for watching.